Awesome. I love your shirt. Okay. Greetings, programmers. This is Jim McKee, and welcome to our Tea, Coffee, and Code session today. Our computers getting smarter, all on artificial intelligence, machine learning, deep neural networks, all of that stuff you hear about and that we get worried about with movies like The Matrix and Terminator and such like that. So, some of the general ideas we're going to discuss today. This is going to kind of be a high-level conversation. This is a coffee shop conversation, if you will, between programmers for programmers. So imagine we're all hanging out in a coffee shop discussing our favorite topics. Hopefully you have a enjoyable beverage handy. And yes, Bitcoin and blockchain, Chris, that is on my list. Actually, I had it scheduled early and then I moved it and then I got to move it back around. But that is one I definitely want to cover. Anyway, so here's some of the general ideas that we're going to cover. A quick disclaimer. This is a coffee shop conversation. We're not giving you any specific advice or anything along those lines. Our opinions are our opinions. We will probably disagree with each other. And if you ask me tomorrow, I will disagree with what I said today. That's just what it is. So I'm going to go through real quick and introduce our panelists. Actually, I will let them introduce themselves. We'll start with Boyan. Boyan, do you want to just say a couple things about yourself real quick?
Sure, absolutely. Well, again, I mean, my name is Boyan, and I have been developing in Delphi since pretty much version 1 in '95, and I have relatively recently become Embarcadero MVP. I have done quite a fair number of relatively large component libraries for video, audio, digital signal processing, computer vision, and artificial intelligence, much to our current topic, logic lab, communication control, and animations, as well as visual instrumentation. I also am the creator of Visuino, a fairly becoming popular software for programming Arduino type of microcontrollers. And in my spare time, I pretend to be running into software. I also do some blogging and some social media, do have some limited social media presence. So that's pretty much about me, I guess.
Yeah, you're always doing some cool stuff with our Arduino and stuff like that. I always joke that if the computer uprising happens, it'll probably involve your software.
Hope not.
I hope not. Next up, Craig Chapman.
Hi, good morning, good afternoon. Like Boyan, I've been using Delphi since about the mid-90s. I've specialized on Delphi for my career. Worked for Embarcadero for about 5 years, and now I'm an MVP. I have a blog which has become quite popular, and I'm actually currently building a machine learning framework, so that puts me a little bit on topic. And that's me.
I love that when we did that user group presentation about your machine learning framework a while back that you're working on, and someone asked why you built it yourself, and you're like, well, it's just like good. Wanted to learn how it works. I love that answer.
Seemed like a good idea. I mean, so the truth is I didn't want to shoehorn Python, so I decided to do something a little bit crazy and write my own kind of equivalent to NumPy. And I remember about 3 years ago, it was probably the same event, and somebody said to me, oh, I've got this friend who wants to write, a NumPy for C++. What a crazy idea. And I just sat there getting more and more quiet thinking, yeah, I'm doing that for Pascal. So.
Yeah. All right, Sergey.
Yeah, hello everyone. Yes, I also a Delphi developer. I'm calling myself a Delphi evangelist because all the time I'm explaining people around me why I have to use and why we have to use Delphi and for which purposes. Yes, I also a Delphi developer, but maybe not. I cannot say that I'm from the mid of 90s. Yes, I started my career with Delphi, and right now I'm in my company working with Delphi. It's not only desktop, it's also mobile platforms. Yes, we're developing mobile cross-platform mobile applications using Delphi. And of course, not only development, I'm participating in different Delphi ecosystem and Delphi world activities, like we are preparing webinars, events, conferences, and so on. Maybe you already saw some of this. And this is why I'm here, because I also have a deep, let's say, maybe not deep, not like other presenters, but experience in developing commercial application with artificial intelligence practices, let's say. It's not like developer artificial intelligence, but of course, some frameworks, some products, and I have what to say. I just have a practical experiences. Maybe it will be helpful to share it with somebody.
Fantastic. Actually, I realized that I've met, so Craig I met Craig when he lived in Texas, but he moved to Boise, so he was right next door to me pretty much now. I met Sergey, is it Belgium? Yeah, we met in Belgium.
Yes,
and then I met
Brussels, yes, on the conference, yes. One time, we 2 continents, and yes, we met each other in one event. Before this COVID, it was 2 years ago, it was autumn. Yeah.
But I haven't met Yilmaz yet. Yilmaz, you want to go ahead and introduce yourself?
I am Yunmasuru. I'm a mechanical engineer. I'm very nice to be here. Thank you very much, Jim. It's a very great presentation. Hello, everyone, again. Sorry for being late. Actually, I am developing software since maybe 1988. I don't know. Before the university, at the college years, started with Amstrad CPC Basic, Commodore Basic, Amiga, Amos Basic, with starting. But for a long time, I'm a C++ builder developer. It's my primary. I am also knowing more than maybe 30 programming languages, but just a little bit for trying, like Palm C, Object C, and other Delphi, Fortran, I am also MVP, T++ builder developer, and writing posts at the Learn C++. I'm gonna show some sneak peeks, maybe in later presentation slides. And I am the founder of the Essential company. We are a very long project, maybe since 1992. We are developing a Braina AI project. It is based on artificial general intelligence. Actually, it's a very hard part. This is why taking a long time. We are working on neural models and other models on it, mostly using C++. And sometimes we are teaching innovation things like Arduino, etc., for kids, students, and young people. That's all. Thank you very much.
Yeah. All right. So I'm pretty sure that when the computer uprising happens, it's going to involve one of you four.
Yilmaz, will you share with us some insights and results?
Yes. Maybe Jim will share a webpage. And
when we have to start scare.
Yeah. So just in case someone forgot who I am, my name is Jim McKee, developer advocate and engineer here at Embarcadero. I've been using Delphi. I actually started with Delphi 2, but I've been using Turbo Pascal for years before that. I just missed the excitement around the original Delphi release. Real quick about me, I don't have any practical experience with artificial intelligence, although I did studied a lot about brain-computer interfaces, and which is something I've always been really interested in and I follow closely, but I have not done any implementation yet, so you can't blame me when the uprising happens. So this is just a list of some topics possibly for the conversation today. If you have questions on any of these topics or other related topics, feel free to put them in the question panel, and we'll do our best to discuss them and maybe answer them. Again, this is really more of a conversation, so feel free to add your comments and such here, and we'll, like I said, try and address those as we can. All the panelists have brought a lot of really interesting topics and information to share as well. So yeah, this is going to be pretty fun. I'm excited about this. There's a lot of things in here that I'm like, ooh, I can't wait to hear about that. So yeah, just use the question panel there on the right, and we will try our best to address those. So I want to open real quick with a little story. When I was, so back in 1980, which I was 7 or 8 then, my parents got me a Commodore VIC-20. I don't know, any of you guys get a Commodore VIC-20? Commodore 64 maybe? I know Craig did. And I knew I was going to be a computer programmer. When I started programming on there, man, I was like, this is it. This is my stuff. And I wanted to, I knew I was going to be a computer programmer. And people were telling me, oh, you don't want to be a computer programmer because computers will soon be programming themselves and programmers will be out of work. And that really puzzled me as a kid. And I'm like, well, somebody has to tell the computers how to program themselves. I mean, that's just how it's going to work. So it didn't dissuade me. I became a computer programmer. But then the really weird, interesting thing is I completely forgot about that really for the most part until 2017. I was in Tokyo for the Rad Studio Delphi Tokyo release. And they had a press event. And I was there at the press event and talking to people, and did a little presentation showing off some of the stuff, new stuff in Tokyo. And one of the members of the press came up and asked me, it's like, well, this isn't a good time for programmers to get involved in computer programming because computers are going to start programming themselves any day now, and they're going to be out of work. And I'm like, okay, back in 1980, I heard the exact same argument, and it hasn't happened yet. So, you know, this is, it's something that it's an ongoing thing is my point, and I don't know that it's really happened yet, and we're getting closer for sure. But in my mind, so first of all, I love this comic here. Basically, in order to describe to the computer how to program itself, you have to create a precise specification, which is what writing code is. So whatever that looks like, that's going to change. Clearly, the way we write code today is way different than we wrote code in 1980, and the way we write code in, you know, the next 20 years is going to evolve as well. The IDE gets better at suggesting things and giving you suggestions. Compiler gets better, more optimizations and stuff like that, and all that can benefit from artificial intelligence. But I still think that the computer, eventually all professions are going to be replaced with AI, but when the programmer is replaced with AI, completely replaced, that's it. Everybody's replaced at that point because the computers will be getting smarter faster than we do. So anyway, I don't know if you guys have any thoughts or comments on that, or I see Brian says he started on a Commodore VIC-20.
Started on a Tandy TRS-80 and then went to C64. Somebody else here was mentioning Amiga computers, and I actually have behind this cut each of the machines that I programmed when I was growing up. I rebought them to display on my shelves here. So yeah, that's very familiar. What you're saying about computers programming themselves, though, there's some interesting technology which I think is about 5 years old now. The program, which I'm going to get all the details wrong, but I think Microsoft is pioneering with their AI stuff. And the idea is to build neural networks which are able to directly tune other neural networks. So effectively to program those neural networks for a particular problem. May not be the same form as, you know, programming as we understand it, but that effectively counts, I think, as machines programming themselves. So it's coming.
It is coming. Yeah, it is something that, yeah, they are doing that. I've heard about that too. Boyan, were you going to say something?
Yeah, I was going to mention that generally speaking, the modern direction, the artificial intelligence, I mean, because artificial intelligence meant different things over the years, and I have brief sight on that. The direction it has taken in recent years is to follow the concept of classifiers. And many of the classifiers, they are self-training one way or another classifiers. They keep learning. So in essence, the direction of artificial intelligence is rather different. The whole concept is rather different than traditional programming. In traditional programming, as shown on this slide, you have a specification, and then you go and you do implementation based on this specification. In artificial intelligence, we are moving more and more in the direction of no specification at all, right? So you start with a blank sheet, and then you let the software to learn one way or another, be it through some form of training or trial and error, to learn to perform certain tasks. So from that point of view, the traditional form of programming does not anymore really apply to at least the training part of the classifiers. And again, of course, it's a complex and long topic. We don't want to dig too deep. There are parts that obviously are still implemented in traditional algorithmic, be it parallel or not, implementations. But many of those parts are now being moved directly to hardware, be it FPGAs or other forms of dedicated AI hardware, not to mention some of the experimental work that has been going with quantum computing. So that means that while we can argue that in order to traditionally program a computer and to have the computer program itself in traditional sense of programming, you have to have a detailed specification, and the best form of such detailed specification is code, as shown on the picture. In AI, this simply doesn't apply anymore, at least in our current direction in which AI is going, because there is effectively no expectation of detailed specification whatsoever. The specification is something that is expected to emerge as part of the training and trial and error or whatever form of artificial intelligence training is going. That's what I wanted to inject here.
Yeah, that is true. Is that it has the whole idea has evolved quite a bit. Yeah.
So one thing that occurs to me when you're saying this, with regards to classifiers specifically, then I guess your specification is your training data, right? So whatever your scenario is that you're training on, where you start to see the specification fall away is with the related technology of autoencoders, autodecoders. So these things, basically the concept of an autoencoder decoder, I think is based on the restricted Boltzmann machine, is that you train the AI on a set of data, and the target for that AI or the target for that neural network is to reproduce the data that you give it. And when it's accurately reproducing the data that you give it, you then chop the neural network in half, because in the middle, the layer in the middle represents what the neural network, the brain, sees as the representation of that data. And this is where a lot of the deep fake technologies and things like that are coming from now, where you train it to recreate a face, and it will create an internal representation of what that face looks like to a neural net. And then you take the output of a different face and apply it, and you're then able to take one face as input and give another face as output. That's kind of how it works. So the specification disappears in that kind of training, but I think from a general automation standpoint, the data becomes the spec, which is a fascinating paradigm shift from traditional programming.
Yeah, that's a really big thing. Actually, I can't remember if I have slides about that or not. The data becoming the spec. But I did also want to bring up that there's a lot of conversation going on around ethics and safety with AI. A lot of Elon Musk and Stephen Hawking and a number of other big thinkers, much smarter than I am, have come out and said that it's a fairly significant threat, just unchecked artificial intelligence could have on society. And everybody's like, well, what about Isaac Asimov's 3 laws, which 3 laws of robotics, whatever you call them, which there's been movies and stuff made about this. But if you've read the book, the book actually is all about how the 3 laws doesn't work. So,
right, and I don't want to inhibit you moving on to the slides, but I am curious with each of the panelists today where you stand on the singularity. How do you think it's going to happen, and what form you think it would take. That does fascinate me, if you will entertain the question.
I don't believe that it will happen, because like the standard question from single people, I think in 5 years we won't have even any software developers. Artificial intelligence will do everything. But according, I don't know, my experience, everything is becoming much more complicated. I don't know. It should be easier and easier, but instead of 5 frameworks, right now we have 200 frameworks. I don't know. I don't believe in this anyway at all.
Right.
You don't think it's going to happen? Okay.
Yeah, I personally believe that Singularity more or less has effectively happened at the moment. We do live in Singularity. We simply don't fully realize it. And again, we live in society where it becomes, as I mentioned, I don't think it was, yeah, I mentioned it before the show started. But I believe that we live in society where human intelligence is integrating closer and closer with artificial intelligence. And artificial intelligence is not in the traditional form we imagine, or Asimov imagined and everybody else, of individual computers being extremely smart. Instead, we have a global network of interconnected artificial intelligence pieces of computers integrated in what is internet, obviously, nowadays. Integrating, on the other hand, with humans, feeding them data, the AI processing that data and feeding those humans back certain data. Even a search engine as such is effectively artificial intelligence piece processing human data and delivering it to other humans. The level of complexity of this interconnected framework effectively is of a level that, in my opinion, competes the level of intelligence of individual human. So from that point of view, I think an argument can be made that the singularity has already happened. We already have something that has a level of intelligence that is comparable, up to a certain extent, with human intelligence. So whether the exact way it represents that is a different topic. It obviously represents that in a social way, but so do all of us. I mean, most of us don't do software development all the time, so we cannot use software development as a judgment of whether or not somebody has achieved human intelligence. So from that point of view, it can be argued that machines have already achieved in some form intelligence that is to some extent comparable to human intelligence.
Right. And the only way to... Sorry,
go
ahead.
Explanation of singularity term in another Isaac Asimov book, Foundation. Like they had spaceships, but they didn't know how to build this spaceships. They have them, but they cannot reproduce or copy them. And this was the knowledge just was lost, and that's all.
Right. And actually going on from what Boyan was saying about it's here now, it's already here in some form. I think the only missing piece to make it AGI in a Terminator sense is the piece that, from the introduction, I think Yunmasuru is building right now. So.
No. Craig, you are also doing. I know you worked a lot. You have, I think, maybe some presentations about it. I don't know.
Oh, I'm just doing the low-level engineering stuff. I'm not getting involved in all that AGI stuff.
Okay.
So what do you think, Yilmaz? Singularity is going to happen? Happened?
I have no idea, actually. I watch a lot videos and papers, reading papers, you know. I can't say anything, but when you open a hole in a wall, if there's a light, you are looking from this view, and if you see something beautiful, something good, something easy to reach that, so you break the wall, you know, and maybe you open the door and you go there. But if there's a very bad thing, maybe someone inserting needle into your eye, from that hole, so you close the hole. So we don't know what will happen about the singularity right now, but we will see.
But I have a couple of clients, they already reached singularity. They have a software executables, but they lost source code. It works, but they cannot edit it to change it.
It's interesting that what you brought up though about like in the Foundation where they lost the rocket ships or losing the source code, that happens a lot, is that I've followed a number of books and YouTube videos that are like how to make everything, where they try and go back and make things from scratch themselves. And one of the things that they found is there's a number of industries where they've built up these layers so much that there is the ability and the knowledge of how to do this that they used to do is gone, because they don't need that anymore, because they've got an entirely different way that's built up over the years. And so if we were to lose that technology, lose that ability that we've built up, then we wouldn't have that platform to start from. So it's an interesting thing that's happening here for sure. So I will weigh in and say I think the singularity is going to happen, and I think that it is it's what it's going to look like. We don't know yet, because famously, so artificial intelligence way back, if you go back, I love reading like old science fiction, like iRobot and stuff, because what their idea of artificial intelligence was is completely different than what it became. And there were things that way back in the day when they're like, this is how we'll know artificial intelligence happens. That's happened. And now they're like, oh, well, we got to move the goalposts because we didn't understand what the actual artificial intelligence was. And so that's what's going to happen, is that we're continually moving the goalposts, the expectations of what that future is going to be. But I do agree with Boyan that we live in a world today that we are cybernetic enhanced humans. Humans are no longer basic humans. I mean, I wear glasses. I can't remember stuff. I have a device that I carry with me at all times that feels almost like it's an extension of me, that gives me access to knowledge, the ability to connect to people and see things far away. That is magic. So
too much information.
Yes, yeah. It is happening. It is happening. So I wanted to also include this here. This is the Gartner hype cycle. So they do this for emerging technologies, but they started doing it now specifically for artificial intelligence as well. And this is where they kind of rate where things are at. Generally, what happens, so most things go through this cycle, and so generally this is the stuff that you hear about all the time, is the stuff that's at the peak of the hype cycle, the peak of inflated expectations. That's when it's in the evening news. That's when your parents talk to you about it, that know nothing else about technology, but they're like, oh, I heard about the such and such. Right now it's NFTs. Everybody's talking about NFTs. But we go through this trough of disillusionment. This is where you buy the technology, but then you stop using it because it doesn't really do what you expect it to do. And eventually we reach the plateau of productivity. So it's interesting to look at this. And then they put these little symbols on it here to say, so this means obsolete before it plateaus. So it says it's not going to make it. The triangle says it's more than 10 years away. Dark blue, 5 to 10, and then light blue is 2 to 5. So I think that's an interesting thing to look at, think about, because it's easy to say when stuff's at the top here, we think, oh, it's here, it's going to be amazing, but until it has had some time to mature. If you remember the Segway, for example, when the Segway came out, it was this, and then it went down here, and it really went from there. So anyway, I'm going to go ahead and go on here, though. Sergey has a slide here. You want to introduce this to us, and we can discuss it?
Well, just like some insights, again, according to my experiences, not all people know the difference between AI and AGI. And this is why maybe Yilmaz more better will explain, because we have only one general term, AI, and everything is like robots, terminators, and just recognition of Excel files is also AI. Maybe Yilmaz will just expand these terms, difference between these two terms. Maybe it will be interesting for the people, the Turing test and so on.
Yeah.
Oh, okay. Maybe Yilmaz will have its own slides later. Yes. Anyway,
you want me you want me continue from this slide? Okay.
Actually, I was gonna.
Because
I'd like to hear also an experience.
Okay. AG. I will repeat again. I think my slides, but AGI is the core of the AI. Actually, it is the basic of the thing. Something like a baby brain. You know, when you birth, you have a brain activating, doing something. You know, it's the something like factory settings of the brain. Or the kernel of the Linux, something like that. It's the kernel of the brain, and AI is the sum of the machine learning and deep learning and all other AI technologies. There is no AI yet, there is no AGI yet, but we are trying to find how we can do this, how we can achieve the best one, the most closest one to the brain.
Generally, AI, it's a science, correct? It's a science. It's not like a business right now.
It is a very deep science, and there is no information about it. Still, we are searching on it, trying different models, different things. What happens when we do this? What's wrong? So it's a very big study, I think, and there is no money about it because
no money. You have to somehow. Yes.
Yeah, but if someone finds, he is the best. He is the best one.
Is it possible like one scientist, one person, or group of three will invent something? It will be like accidentally, or it will be like systematically. What do you think? Is it possible? It should be 1,000 people. Is it possible, like one guy, you know that all we are developers, I will take computer, I will go to the village and will write some code that I believe that. Is it possible? What do you think?
I think it is possible because I am watching natural movies, nature movies like Birth of the Animals, something like that. It is finding himself in a new world, and it is adapting himself very easy, you know. So if he find the core of the thing, so all the AI can develop under this core kernel. With this core kernel, it can adapt, it can shape, it can get skills by itself. But it is a very hard part. We are trying to simulate how we can do this. Actually, you steal my slides now. I will explain at the end if you.
Yes, we'll just
we could do slides.
Yeah, because I'm more like from practical side, on practical dark or like light side. I don't know. Like I'm just and sometimes it's too boring. It's too boring. But you're like. Yeah, you're romantical, like developing our AGI. Looks interesting.
No. There are some results actually. AlphaGo 0 and the IBM Watson is not closest maybe, but it is something like AGI. They are adapting their algorithm, their artificial structure to any concepts. Very, very successful, especially AlphaGo 0 is very successful about it. And maybe in the short time, we will get more successful results by the big companies.
But Watson does not have, I think, consensus anyway, because that's the question, like that's the core, I guess. What does it mean at all? Okay, let's go further, Jim, because
I did want
to. You can go ahead if you wish, Jim, but I was just going to disambiguate a couple of terms here. So.
Yes, please do.
So I hear AI, machine learning, and AGI all thrown about as kind of the same subject, but they're actually subsets, effectively. So when I was in college, going way back, I'm not going to age myself, but a long time ago, we were told that AI, artificial intelligence, really is a much broader term than what we use today. It encompasses any behavior that you have a machine do, which is intelligent in inverted quotes. So, you know, a machine that stops itself from running a human over by reading a sensor and making a decision to stop. This is an intelligent behavior and counts as artificial intelligence in the broader sense. Machine learning, on the other hand, which is almost entirely neural network-based technologies, machine learning is this field whereby we have problems that we want to solve, but it would be incredibly difficult, if not impossible, for a human programmer to write an algorithm to do it. So what we do is we train a machine to do it. We write an algorithm that can be tuned. It's called a general function approximator, and you can tune this function to approximate the function that you need. That is machine learning. In definition, is a machine that learns. And AGI, as I understand it, is artificial general intelligence, is effectively a machine that has a form of intelligence that is generic. So you could say to it, hey, go do this, and it would be able to figure out how to go do this, right? But within the field of AGI, the advances that we have right now are more limited, of course, but AlphaGo has been mentioned, which is an AlphaGo Zero, which all derive effectively from the older DeepMind research. That was trained on video games initially. And the idea was, if humans learn by playing games, whether they are video games or real world experiments, if we can train an AI, a machine learning algorithm, on playing video games in a generic way, then we are taking a step towards this artificial general intelligence, where we can say, hey, go make me a cup of tea, and it will go make you a cup of tea, hopefully without treading on a baby along the way, you know. So just to disambiguate, AI is generally these days conflated with machine learning, but it's actually a much wider field than machine learning specifically, which is where most of the advances are being made.
Yeah, that's a good point. I was going to point out that there's a lot. So a lot of the stuff you're talking about here, though, are things that used to be considered things beyond the possibility of computers doing that they're now doing. The Turing test, for example, it's pretty easy to have a conversation with some of the more advanced, GPT-3, that it's indistinguishable. You can't really tell the difference between a person and it. You know, there may be some, if you get really tricky, figure out ways to do that. But our concept of things that were impossible for computers to do has changed, that to the point now that we need to come up with new, like I said, new goalposts for it.
Right. And with regards to the Terminator Singularity AGI scenario, which, you know, anybody actually practicing in the field knows that that's not a real thing right now. What Boyan was talking about is an interesting perspective on it, but a different thing. And it's not really a thing, but when we ask how close are we to it, well, a lot of the machine learning algorithms we have today that can say image classifiers, we've got image classifiers in medical technology that can outperform humans, right? And when you take a look at that, video game playing DeepMind outperforms humans in playing video games. AlphaGo beat Lee Sedol. All of these different sort of fields of technology are able to outperform humans in their specialized areas. And then I think to myself, well, how much hardware is involved in running them? Training them, that's a different matter. That takes massive hardware. But most of these algorithms run on a GPU. So the only thing really missing, and I say only thing, I don't mean to reduce the field, but the only thing really missing is that AGI strategic component in the middle. And if that fits on a GPU, well, then the old thing of AI will need massive compute power, that goes away, because we'll be able to run it on a handful of GPUs, right? So yeah, a lot of things that were considered impossible a decade, 2 decades ago are now commonplace.
Yeah, the deep dream stuff, I will. I remember there was a movie, Short Circuit, back in, I want to say 90s probably. And
Johnny Five is alive.
Yes, Johnny Five. And the thing that that convinced the guy that Johnny Five was alive, that Johnny Five was conscious, is that he put the soup on the paper and showed him to pick the ink, the blot of the soup. And he's like, oh, it's soup, da 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 da. But it looks also kind of like a butterfly. And he's like, oh, yes, if you can see a butterfly in soup, you're therefore conscious. That is not something a computer can do. And that's something that, that we used to say, is that computers can't see beyond the limited data, the limited, the reality, right? They don't have imagination and stuff. But when the deep dream things come out from the Google classifier, which I haven't seen deep dream, go take a look at that. And they're able to say, show it a cloud and say, do you see a dog, or show me where you see a dog. And it's like, oh yeah, right here, this cloud looks like a dog. And you're like, oh, yep, you're right. It does. It can see a dog in the clouds. And now we're like, oh, it's just using data. Well, that's something we used to say they couldn't do. Yeah. So it is a constantly evolving thing.
That is now practically an example that a teenager can script together with Python in his bedroom, right? That is, not to diminish teenagers, but that is something that is now relatively trivial to do, which is startling progress.
Okay, I think that maybe the future is a combination, as the next step, combination of neural technologies and AGI. Like you will combine these two things, because we cannot invent this physical, this physical part. Maybe it will be like implement this still something which we like consensus on the physical part and apply side some device, not like human, just grow up this brain without other parts of the human. I don't know. Maybe it's too scary, but who knows?
Yeah, well, the question of should we is a big question.
Yeah, well, this actually brings very interesting topic about, again, the singularity, the fact that AI has become better in some specific areas, as Greg pointed. Well, we probably already really are in the singularity, because recently they, about a year or two ago, they did try to use AI to effectively replace lawyers and compare the performance of AI against lawyers, and AI outperformed them. So if AI has outperformed the lawyers, well, we by definition have achieved the singularity, because the lawyers are the ones that pretty much decide those type of things, aren't they? So in the court, we have effectively lost the battle.
Well, yeah. So right now, there's a lot of specific intelligences that can accomplish certain tasks better than humans, but there is not one integrated one. And one of the things that we have a huge problem with right now, there's two things I think that are really big that are holding us back from a singularity today. One is that all these things are split into multiple silos, and there's no integration between them. So for example, I have a Google Home and an Amazon Echo in a couple of rooms in my house. I like the Echo better. I think the Echo is a better product overall, more usable, but there's some things I like better about the Google Home. There is no direct integration between the two. And there's so much technology out there that, depending on which camp you're in, if you're in the Apple ecosystem, good luck getting anything outside the Apple ecosystem. I remember the joke was when Apple introduced the ability to have push notifications from Twitter, everybody joked, oh, did Apple buy Twitter? Because it's a very closed ecosystem. Facebook's got their own ecosystem. And right now we're really held back by the fact that all this stuff is in these individual ecosystems and there's not much integration. So integration is holding us back. And the other thing that's really holding us back, and I think it was Boyan that talked about that the data is what's programming, right? The classification of the data, and because we are providing the data to the systems for them to learn and become these machine learning systems, the limitations in the data we provide them and the biases from that data is also holding back the systems from being able to achieve more than they would otherwise.
And actually, I'd like to offer a counter to your point there, though, because so with regards to integrating the silos, this has already started happening in some very interesting ways, particularly in medicine. And a lot of things happening in medicine until very recently, the industry was kind of set in the past, right? I mean, data was shared among facilities by CSV, if it was shared at all, or by fax still, right? A lot of medical research and hospitals and various institutions in the medical industry just weren't talking. But when the data scientists came along and started trying to run predictive models using medical data, what they did was go out and try to collect that data from the silos and bring it all together. And a lot of the advances that we've seen in medicine that are machine learning related have come out of things that the machine learning algorithms have noticed, have identified, that we never would have noticed even if we'd brought the data together ourselves, but certainly not without bringing that data together. So a lot of that is starting to happen. I think what's actually holding back the technologies that you're speaking of, like the individual devices not sort of integrating with each other, is also a thing that will hold back AGI to some degree. And that is, it's got to be a viable product, right? We're not making AGI for the fun of it. We are making it for practical application. And if there isn't a product that can be commercialized and we can make money from it, then it's going to be a lot harder to get that developed than if there's a product behind it. So I think the singularity will happen if we can find a way to make it worth money, and then we have to. I think we'll then have to find the answers to the question: should we have turned it on? Right. So,
you know, that if you look back in history at Tesla versus Edison, and there was a lot of things that both. A lot of times we like to villainize Edison and say Tesla was a genius. But there were a number of things Edison did well as well. But one of the big fundamental differences was that Tesla would chase things purely for the science, whereas Edison would see things, only things that were marketable, that it could be a viable product. And you might argue that that would indicate a flaw in Edison's character. But realistically, is that if nobody wants to pay for it, no one wants to put money into it, nobody's interested in it, and it's not going to do. I mean, it's not to say that you couldn't discover something that nobody was interested in that would do good for society, but if it doesn't ever get adopted, doesn't ever get used, you know, is there utility in it? So, you know, the money in it can be used as considered as a measurement of utility.
right.
Not always the case. I do want to follow up here. There's a lot of great comments here in the question panel as well. So trying to do both things at once, but there was a I would want to follow up on a question you asked Craig on whether or not one person could do that, right? Could revolutionize, could make the breakthrough, push things forward. I would say yes, and there's three things I think that are going on. One is you said is, you know, should we, you know, if singular, or someone, I can't remember, I think it was Craig, I can't remember who it was actually, said if the singularity is dangerous, or if this thing is dangerous, whatever it is we're going to do, you know, some level of AI is dangerous, should we or should we not do it? At this point, I would say we are past the point of no return, in that somebody is going to eventually do whatever this is, whatever this thing we think is scary is. But some people would argue that the singularity, the artificial general intelligence, is an arms race, and whoever reaches this goal first is going to be the only person that reaches it, because it's going to shoot them so far ahead that leave everybody behind. And the problem is today, first of all, there is a huge glut of libraries available. We haven't really got into much on libraries yet. So like you said, a teenager can do the simple stuff in their dorm on their laptop. But also the rise of cloud infrastructure, and the fact that anybody with a credit card can go online and get a bunch of GPUs and have a huge supercomputer going in a matter of minutes. I mean, all that stuff is a solved problem. And so, you know, it's really a simple scenario to work out that somebody could, you know, take the resources available to them today and have a huge impact a single person could. So it's a interesting situation because of the fact that it could be any person, and they could leverage the existing resources. And if it's right, if it's true that that is an arms race, that they're the first person to get there, winner take all, then, you know, if other people are not pursuing it to prevent a bad actor, potential bad actor, from getting there, then that can be a problem.
Actually, this happened before, Jim. When there was a facet machines, do you remember calculating for accounters? Facet, very old machine, and
Yeah.
it was helping to calculate, and all accountants said, "Oh, we're gonna lose our job," you know. And then calculators happened, and they said, "Oh, it is taking our work," you know, because they were calculating by the pencil. And then computers comes, and everybody said, "Oh, everything is automatic and internet-based accounting applications here now." But still, they are very busy. They are doing a lot of things. They are using these programs. They are using things. So there's no afraid about the artificial intelligence. It is something like these tools that will help us, but we will also develop ourselves with these tools. I am thinking very old era, Stone Age, maybe first human in the Homo sapiens, in the first human, and they discovered the fire, you know, and maybe there was a meteor dropped to the earth, and they see the fire there. Maybe they see the fire on the lava. Maybe they try to jump into the lava. What will happen, you know? And they were trying to discover, and maybe many of them that maybe they burned their village by mistakes. Maybe they do a lot of things. So this is a learning process, and in a short time there were happening about gas problems, explosions, you know, we are not able to control. There were train accidents, you know, but we are reducing the things. So learning process is growing up, and everything is getting better. At the beginning we have mistakes like today's happening in AI, but it will be good, I think.
Well, the exception really in machine intelligence is, you know, every tool that mankind has developed from fire and the axe up, every tool has needed the human operator. And going forwards, where we are with machine learning today, we still need the human operator. In fact, the technologies that are being developed are, as I said, generally products, tools that we can make use of. At that point, at that singularity point, if and when it comes, that AI is able to operate itself, well then humans are no longer needed in that piece of the puzzle. And as Boyan said quite rightly, we are now all parts of that system. We're part of the data gathering and the collection and everything else. And we are already today being fooled. I mean, you think of fake news and this kind of stuff. We're already being fooled and manipulated by confirmation bias algorithms and all this kind of stuff. And so the fear, I think, is a legitimate fear. I don't think it's going to happen tomorrow. Despite the democratization of technology, I don't think that somebody's going to accidentally create a brain, right? This would have to be very intentionally done, and from my perspective would take an awful lot of man hours and resources. But the day that comes, that's when we have to be fearful, because that will be the first tool that doesn't need an operator. And more to the point, there's this, I think it was an Asimov problem actually, of once you turn it on, if it is a self-autonomous, self-acting being, it doesn't want you to turn it off. So how do you turn it off? Because it's going to do everything it can to survive to prevent you doing that. And this is where the typical Pinocchio stories like Short Circuit come about, is we want to turn this thing off and it wants to survive, right? So that's where I think the difference will be is AGI.
That idea of a system that doesn't want you to turn it off, the TV series A Good Place, Janet is this.
A Good Place, yeah.
Yeah, she's not a computer, not a robot, but she has a reboot button, and she's like, oh, I need to be rebooted, here's the button, but just so you know, I'm programmed to try and talk you out of it. And so they go to try and reboot her. She's like, no, please don't reboot me. I don't want to be, you know. And so it was just really interesting. I mean, just to think about it from that point of view is if a system that we can relate to, that can emote to us, and that we can assign, you know, that we believe to have consciousness, or we believe to have emotions or feelings, if it asks us not to, that can be enough right there in of itself
Will we want to?
yeah, to make it so that we're not able to, that we have to ask that moral question.
Well, it's interesting that I took the argument of AGI and being fearful of it because I actually stand on the other perspective. We've seen already things like robot dogs as pets and things like this. AGI could be our pets. We could eventually conceivably come to think of them even as offspring, as equals in society, as offspring and stuff like that, and willingly hand the world to them. But yeah, I think from a practical standpoint, AGI is a long way off, and yeah, probably not likely in the near future, though. Prove me wrong, right? It'll happen.
If we look at the nature, we are actually winner on the all against things. You know, there's lion, elephant, very big. You know, but we learn somehow to survive with them, and we also learn how to help them, how to feed them, how to investigate them. So human is very great, and they achieve the things to make them better, and they are the winner. So if we develop an artificial intelligence, I think we will be the winner, like this example. And because we maybe we will not accept reaching against us. I am not meaning dimensionally, I'm not meaning the speed of the intelligence or calculating, achieving data, etc. I'm meaning if there's something problem in AI, somehow humanity will push that thing to, if they see it is dangerous, they will push it, because we are the human.
Yeah. yeah. I honestly, I think that AGI, as far as Singularity and AGI and stuff like that goes, I think that we will see it as, it'll start out as a pet, and then it'll start out as a companion. And I believe that eventually it will become the, you look at things like Elon Musk's Neuralink, and you know, you think about how, like I said, how symbiotic we are with our smartphones today. I think that the future, the evolution of what it means to be human will be intertwined with cybernetic AI enhancement. Yeah, it will definitely be that. I think that our concept of what it means to be us will merge with the idea of something in the computer, and that will be the evolution of humankind. Will not be recognizable from today.
Right up until the day that I say, go fetch my laundry, and the AI says no. If you've got any idea how much I yell at my Google for things it doesn't want to do, when AGI comes, I'm in trouble because Google's going to be out for me.
Well, I mean, I think it's gonna be the other way around. The AI is gonna tell you to go and get your laundry.
Yeah, but precisely my point. When I say go get my laundry and the AI says nope, you go get it. On that day, then the war starts.
There's a couple of questions here I just want to skim through here real quick before we move on. I've been trying to answer some of them as we go, but some of them I do want to bring out to the panel here as well. James asked, how will the proposed EU ban on AI affect the development of AI and the production of current software? I don't know that they have a proposed ban on general AI, although I could be wrong. I know there's a lot of bans on like facial recognition systems and stuff along those lines. So my opinion, and then open to what everybody else's thoughts on this are, is that the genie's out of the bottle, as it were, that if one nation tries to limit this, it'll just hold that one nation behind, and it'll happen elsewhere. And if it doesn't, even if all the world governments come together and try and put a ban on AI, all that'll happen is we just won't hear about the development that's happening. Is that it'll still be going on. It's doesn't need government funding. It doesn't need public awareness to continue to happen. And there most likely is a lot of development going on that we're not aware of. I'm not trying to be a conspiracy theory person here. I'm just saying that's kind of the reality, is that it doesn't have to be something we're aware of. Does anybody else have any other thoughts or comments on that?
Well, you ban something in general from history, it always moves on the world. So the only thing that this could achieve is to create another black market and more gangsters in general, this time involved not with drugs and drug trafficking, but instead with AI work. And yeah, I mean, it only is going to lead to increased crime. That's my opinion.
You say not related to drugs, but there is a functional AI being used today to grow a certain substance, which is only legal in parts of the United States, right? So,
sure.
Yeah.
Yeah, the regulation can have some impact, and we do need to find the right balance. We do need to have rules around facial recognition and stuff like that. That's for sure. I'm definitely not anti-regulation, but we do need to have regulations and such. But we just need to figure out the right way to do it. What's the easiest way someone to get started with machine learning and Delphi? I know Boyan has some libraries and some other things out there. I'm curious if any of you have any comments. I know Craig's library is not available yet, so when Craig's library is available, that's one option. What would be suggestions? Boyan, let's start with you, since I know you do have a library out there. Do you want to talk real quick about your library?
Sure, yeah. I mean, I did it quite some years ago originally. So basically, I became fascinated with classifiers specifically, because I still believe that this is the most advanced and the most promising field of artificial intelligence, at least at present, even today. So I basically started experimenting with some classifiers. At that time, my wife was going to UC Berkeley and taking a course on AI. Oddly enough, the way they were looking at AI at that time was from the point of view of agents. I disagree with, I mean, personally, I disliked the approach that Berkeley had taken at that time and the way they were focusing on AI. And I started instead myself to take some of the things that they were teaching her and exploring them and interpreting them from my point of view of classifiers. And then I started implementing the algorithms at that time in the form of Delphi classifiers, and that's how I created my first intelligence lab version. So it was a Delphi implementation of a few different classifiers at the time. And then other people started contacting me and asking me whether or not I can add some other classifiers. I started to look at some of the classifiers implemented in OpenCV, and I started implementing them natively in Delphi. And finally, a few years ago, I started moving into GPU, and more specifically, I started working with OpenCL, which is one of the open computing platforms, basically. At that time, and even today, there were two of them. There was CUDA, and there was OpenCL. And CUDA, I believe, still is NVIDIA-only platform, where OpenCL was available for multitude of GPUs, and I wanted something that will be available for a variety of GPUs. So I started porting some of the classifiers to utilize GPUs whenever the GPUs are available. So Intelligence Lab, at least for some of the classifiers today, you can run it on a single core CPU. You can run it in parallel on multiple cores. It's a parallel artificial intelligence implementation. Or if you have a OpenCL enabled GPU, which pretty much is any GPU nowadays, including the built-in Intel CPU GPU, right? So we have CPUs that have built-in GPUs from Intel. The Intelligence Lab will be able to perform the classifiers that are OpenCL enabled to perform them on the GPU. And even it will be able to utilize a multitude of GPUs to perform the computation. I have been exploring the direction of having some of the classifiers being able to be offloaded to a cloud type of platform. I haven't done that yet, mainly because of me being involved with so many other things, especially with Singularity. But that is area that I am still exploring in order to, the idea is to have a classifier that can work on your CPU, on CPU and GPU if both are available, and hopefully in the future on CPU, GPU, FPGA, or multiple CPUs and GPUs across multiple systems in a effectively network. So that's the area where I'm researching for future development, and I have done some of the groundwork for that. I simply haven't had enough time to move to the next step. So that's what I have been doing with artificial intelligence. And of course, I have the more traditional vision lab, which has a limited and relatively specialized type of artificial intelligence, still part of it based on classifiers, that is specifically focused on things like facial recognition and object recognition, so mainly in the area of computer vision. So that's what I have been doing up to this point with AI. And just to veer a little bit on the topic of Delphi, I am also working to add some limited AI capabilities in my Visuino components. That's another interesting area where I'm working. So at least some limited neural networks, if not other types of classifiers, hopefully will be available later this year in Visuino as well.
Fantastic. I will point out, I put a link in, or a comment about the Python for Delphi library, which will let you leverage the Python TensorFlow library. So interestingly, TensorFlow for Python is written in C, C++, so it's a native library written with a Python interface. And so the Python for Delphi library lets you leverage that directly. So basically it makes it compatible with any Python library. So at that point, you're using Python doesn't really part of the equation, and it's just the interface between the libraries. So that's an option there as well. There's some resources out there about that. Anything else anybody would suggest as far as if you're a Delphi developer want to get started with machine learning?
By the way, if you have a Delphi, we have the API for all of these cloud services, even for TensorFlow.
Yes.
We can do everything almost. We don't need a physical TensorFlow device or hardware. Everything in the cloud, and using just API, we guys can access everything for now. We don't need some library on our machine, because you won't have enough time to understand how it works under the hood. You will just need the results of this library.
That is true. Yeah.
It depends a little bit, because there are cases where you, for a variety of reasons, cannot rely on the cloud. Autonomous operating devices have to be able to operate even underground in a cave, let's say. And a few years ago, I was involved in developing a system for detecting drownings in swimming pools, right? So the system has to operate even if there is no internet there, right? So because you cannot allow somebody to drown just because you have lost temporary internet connection. And again, if you lose your internet connection for 3 minutes, if you're doing analysis on some business data, nobody cares. But if you lose internet for, let's say, 2-3 minutes for whatever reason, and somebody drowns, well, I mean, that person is dead, right? So from that point of view, yes, it was written in Delphi, and yes, that was big part of why I ported some of the functionality on the GPUs, because I needed all of the performance in a portable machine that you can put next to swimming pool, and that machine will be able to monitor, perform all of the visual processing, obviously, with my libraries, as well as detect the event of somebody drowning and alert immediately the lifeguard. So again, you can argue that you can do nowadays everything in the cloud, but there are cases where you cannot rely on that. Let's imagine that you are in autonomous driving vehicle, right? And you lose internet connection even for a couple of seconds for whatever reason, just because you're going through a tunnel. The fact that your car crashes is gonna mean that you will at least have a damaged car.
Yeah, boy, I think that it's good to start with cloud because you don't need a lot of resources.
Sure.
After that, I think people won't have such questions.
Agree.
What I have to use
Agree.
with Delphi? They
Agree.
will be already familiar with the system.
Understand.
I would also
Yeah.
I would extend to that also. It depends on what you mean by get started, right? Because if what you're talking about is how do I learn to use and consume AI technologies, then the cloud's a great place to start. If what you really want to understand is the underlying technology, which is how I ended up going down the lengthy road that I did, then you really will benefit from having something local, something that you can get your hands on directly. So it really depends on where you're going. And I would like to take a stab at it. Either myself or Boyan might be better suited to answer the question of the follow-up question of what is a classifier.
Yes.
And I'll take a stab at it, and Boyan will probably be far better suited to it. But in machine learning, there are several categories of problem that we have the machine learning algorithms solve. One of those categories is a regression problem. So you take some input data, and there is a relatable output for each of the input samples, and you train the machine to understand how to map the input to the output. So that would be a regression problem. A classifier is a little different. It's where you take some input data, and each sample in your input data has one of a number of categories that it can be applied to. So this might be, here's an image. Is it an image of a leaf, a car, or a person, right? So you've got 3 possible outputs, leaf, car, person. And a classifier does the work of saying, well, I think that's a person, I think that's a leaf. So that's a classifier problem. And then the third kind of problem is, or not so much a problem, but is generative AI and generative machine learning, where you are generating new data, completely new data based on some sample data that you feed in. And this is where you start to see things like machine learning algorithms generating its own music, or inventing photographs of people that never actually existed, and that kind of stuff. So that would be generative AI.
Yeah. Yeah, sure. Basically, the way I looked at classifiers, I'm looking at them from a more generic point of view. So the way I personally define a classifier in my studies of an expression of artificial intelligence, it is a box. I mean, it doesn't matter what's inside that box. You feed it certain features, certain information, and it gives you certain results based on this information and based on a training that it has. And that classifier can have a self-evolving training. It has to be able to train one way or another in order to be a classifier. And it could be self-training. It could be something that has separated manual training. So that's how I personally define classifiers when I talk about AI and classifier-based AI. And again, from the way I am presenting it, it covers all the three problems that you mentioned. So that's why I kind of group them into the very generic concept of classifier. And the reason I picked such a concept is, again, here I have on this slide, there is a brief history of how the general public understanding of AI has gone and the general directions. I mean, we all started, that was on the previous slide, by the way. We started with the expert systems, and yeah, in the 80s, expecting that we can take the knowledge of a person and code it with fourth generation languages to mimic the specific person, just simply by entering the knowledge of that particular person. That all bombed quite badly, if anybody remembers those old days. Then we move to things like planning engines, when we try to find paths through mazes and stuff like that. That's relatively a specialized type of classifiers. Here I'm not mentioning the agent-based classifier. I mean, the agent-based AI, which Berkeley was pursuing at the time my wife took the courses. But their agent-based AI is very close to planning engines. They were looking at an agent that you place in a maze, and that agent discovers its way through the maze. So I would argue that they were still looking at it from the point of view of planning engines. And then we move to the more modern time, in my opinion, where we're largely talking about classifiers. And now, Jim, you can move to the next slide. And this is what I meant by classifier when Jim moves to the slide. We'll be able to see it. Yes, right here. So this is what I mentioned earlier. Concept of classifier is a device, it's a black box, it could be a piece of software in our case, that receives certain features, certain information about the data. So typically the way a modern artificial intelligence system works in general is you have the data, you have what's called feature extractor. You're looking at specific information about this data. It could be the color. If it is a picture, it could be the color of each individual pixel, as example in the picture. If it is audio, it could be the different frequencies in the audio over a certain period of time, Fourier transformation over time. You take this, you feed it into the classifier. The classifier receives that information about the object in numerical values, makes a decision of what it believes this data represents, and sends you in the output different conditions, information about what it believes the data contains. And the classifier can be self-training. There are different types. They can self-train based on trial and error feedback, or they can be pre-trained and then rely on pre-trained data. So when you're training them, you will feed data. The feature extractor is going to extract the features. You're going to feed them in the classifier, and you will tell the classifier what it is looking at. And then it's going to send you conditions. In self-training adapting type of classifiers, you will keep sending different data. The feature extractor is going to keep sending the features to the classifier, and then the classifier is going to give some output, and then you simply will say whether or not you're happy or not happy with the output it's giving you. So it will try to give you a different output until it starts giving you output you're happy with. And then there is a third type of classifiers that do not take any training. They're called clustering engines. Typically, they will take some data and they will try to organize that data the way the classifier decides completely on its own based on some similarities it discovers in the data. So it goes through the data, it discovers significant similarities between different parts of the data and groups them together and gives you result in the form of clusters of data. So it gives you the same data, you feed it, but it outputs it in organized form. So this way you can see clusters of data. And that's probably very suitable for things like medical research, where you feed a large number of patients, and then you discover certain similarities between those patients, indicating a similar type of illnesses or anything else. So that is how I personally understand classifiers, and I try to explain them to the general public. And that's how I look at them where I work with artificial intelligence. And one final note here, yeah, again, on the same picture, when we're talking about the feature extractor, the feature extractor itself can be implemented as a classifier. So effectively, you can create a multi-layer artificial intelligence system where one layer serves as a feature extractor for the next layer of artificial intelligence. We can go in more details about that, but that's the general idea. I'll give a typical example. In case you're doing facial recognition, you can have one classifier that extracts the location of the eyes purely and nose. Another classifier that will take that information and try to recognize the specific face. So this is a simple example of multi-layer artificial intelligence classification, where one classifier serves simply as a feature extractor for the next layer of classification. And again, there were many different types of classifiers. There are neural networks. Here we were, for a variety of reasons, largely focusing on perceptron-based neural networks, which are typically considered single-layer neural network with single hidden layer neural network. There are much more complex neural networks, including recurring neural networks and temporal neural networks. That's a very large topic. There are other type of very popular classifiers and extremely useful, like naive-based classifier. There is a hidden Markov model, kernel methods, support vector machines, KNN, k-nearest neighbor algorithm. By the way, KNN in the early stages of speech recognition, KNN was the dominant type of classifiers for speech recognition. There is a mixture model classifiers. Decision tree is one of the oldest one, and probably some of you in the old days of software development have at least implemented decision tree game, where you decide what kind of animal it is, whether or not the animal has long ears, or it can jump, or it can bark and stuff like that. Then there is the linear classifier. Self-organizing maps are interesting because self-organizing maps are clustering type of classifiers, and I already explained a little bit about clustering type of classifiers. And there are generative topographic maps, and there are probably many. Did I mention the radio-based function? Well, I'm missing one here in the list, which is quite important. That's the radio-based function classifier. I have just missed it in the list. So again, there are many other type of classifiers that serve a variety of purposes. Can move probably to next slide. So neural networks, yeah, here we have many more people than just me, so probably everybody else can also interject from this slide forward. But in essence, the neural networks are designed to simulate in a simple fashion how the human brain is implemented and works. One thing which is important, and I will interject it as a distraction, but it's a very important and related topic. There is one major difference in the way a human brain works and a computer-based neural network works nowadays. Computer-based neural network always will perform exactly the same way once trained as if you feed it the same data. The human brain, it all boils to data transmission. The data transmission between the different neurons of the neural network is guaranteed. It's 100% the same. So the data from this neuron will be sent to the next neuron without any damage to the data. The difference is, according to studies, that the human brain is very noisy, especially my one. I mean, I have a lot of bugs, obviously, in my brain all the time. So because the human brain is very noisy.
Looks very fine.
Pardon me?
Looks very fine. Your brain looks very fine.
The bugs have flown away already? Okay, well, that's bad. That means that it's empty pretty much here now. But it's okay. It's early in the morning. I will fill it with some coffee. The thing is that because the brain is noisy, there is a very low data to ratio, I mean signal to ratio coefficient in the transmission of the data. For that reason, in the human brain, effectively a connection between the different areas of the brain is implemented in a parallel form. It's been transmitted through more than one lines of data. And the receiving end receives that and attempts to restore the signal. That means it improves the receiving of the signal, but because the transmission is so noisy, the same transmission will never be received exactly the same way. So as a result, the human brain misfires effectively. That's where imagination comes from. So effectively, our knowledge every time gets distorted when we try to process something based on that knowledge due to the noisiness of the human brain. That is one distinct difference between our current implementation, typical implementation of neural networks in computers, and how it actually works in the human brain. Obviously, the other difference is that the human brain internally evolves, and that's another area where I have been trying to do some research of my own in terms of self-evolving neural networks, but that's an area where I simply have not been able to put enough effort due to my overload with everything else. Again, let's return back to how neural networks are implemented in computers. So they simulate up to a certain extent how the brain works. They consist of neural networks. There are two typical types: feed-forward, which is almost exclusively what we use today, and which is a very, very limited and, in my opinion, crappy form of neural network because it's not temporal by definition. But they could be feed-forward or recurrent. Recurrent neural networks are extremely understudied, as the best of my knowledge. Very few people or researchers have done any real studies on them. They're poorly understood, and they, in my opinion, offer the biggest promise, especially self-evolving recurrent neural networks. Hold, in my opinion, the promise to a real artificial intelligence. But again, that's my personal opinion. The feed-forward neural networks usually use backpropagation to train. There are different forms. Resilient propagation is one of the forms of backpropagation, but they are roughly doing the same thing. So maybe next slide. And see what we will be talking next. Oh, by the way, anybody wants to inject something on the previous slide? So anybody else wants to say something?
I'd run a couple of points for you, but I think of neural networks and classifiers with slightly different terminology. So essentially, what I call a neural network is not just the perceptron type neural network, but pretty much any technology based on it, which includes convolutional networks, because convolution I consider as just being layers within a deep perceptron effectively. So I use the term neural network, and neural networks are the basis of the vast majority of specifically machine learning algorithms. Not necessarily AI algorithms. There are classifiers, as you mentioned, which are algorithmic in nature, which do the nearest neighbor and that sort of thing. But one interesting point that you mentioned that I found very interesting was saying that you think that the source of imagination is random firings of missed data effectively in the network. I remember when Google first did that experiment, they fed a neural network all YouTube videos. They just fed every YouTube video into this thing, and then asked it to generate something without feeding it any input. They just said, "Give me something," and it drew a cat. And when they looked at this image of this cat, they couldn't find that cat anywhere in the source data. What it had done is trained itself to identify the features that make up a cat, and then drawn its own cat based on whatever was in the those features. And so I think that that actually is a much better parallel for imagination, and that really what comes of human neural misfiring is much more, that noise leads to messier decisions, okay? We're probably less accurate, which is why we keep getting outperformed by specialized AI, and less logical. And I like to tell, when my friends say things like, you know, from the movies, oh, a machine won't care about you, it'll be brutally logical. And I like to say, well, a calculator is brutally logical. It's not brutal logic that makes intelligence. It's actually something of an illogical thing that makes intelligence. And so that was really the thing that I wanted to pick up on. And then the one other point about researching recurrent neural networks. I believe that GPT-3 and its predecessor were based on LSTM, long-term short-term, which are effectively a variant of recurrent neural networks. So that is a fascinating area where they are being researched quite heavily, worth looking at. Most of the mechanisms we use to put new layers into neural networks, things like convolution and all that kind of stuff, most of that is actually to combat the problems of gradient descent in backpropagation. So while most of these networks are still trained using backprop, and we really are looking for something better, most of these technologies, I think, have evolved as a way of trying to get out of the problems of gradient descent. But there's my 2 cents for the sake of putting it in there.
Anybody else wants to say something?
I agree with you, Boyan, about the. Can we back to the slide, Jim? About the feed-forward networks are mostly used, yes, and yeah, and the recurrent networks are like something like, maybe, not sure, but maybe the idea of the artificial general intelligence, because our brain is working something like that, not like feed-forward networks. And so maybe there should be more research on recurrent networks and maybe combination of them, I don't know, but currently it is not helping us. And our models in Python and etc. all working with a huge of that data and calculating everything, you know, and so it takes a lot of time using a lot of CPU and GPU. Also, there is a possibility to do something very simple. I don't think calculating those too much things helps us. So there should be more research on this. This is what I want to add.
And I mean, bear in mind also that neural networking technologies, we like to say it's based on the human brain, but it isn't. Neural networking technology is based on some concepts taken from biological brains, very few concepts taken. Generally, actually just the idea of a spiking neuron is more or less the core of what we simulate in neural networks. And the similarity between biological brains and artificial brains diverges all the time. I mean, no organic brain is arranged in layers, right? We arrange in layers because of the engineering constraints of having to feed data through what is essentially a series processing device in parallel, right? So we arrange in layers so that we can sequentially process each layer, which in a real brain is unnecessary because it's entirely parallelized. And so I kind of refrain now from drawing the similarities with brains. I like to just say inspired by biological brains. Although, to counter my own point, many of the advances, such as I've mentioned, convolutional deep networks, many of those advances came from observing natural brains and trying to steal concepts from them. But they are quite different things in a lot of ways. I don't think that's a bad thing, because by the very engineering nature of neural nets, they have to be different, right? And you very often come across this with people that get excited in machine learning and AI of trying to solve problems using a machine learning algorithm where a hard-coded algorithm would be just as good. And I watched a couple of videos on YouTube of a guy making an AI that played a video game, and he was feeding in the positions of the objects that were in the game into this AI for it to play. And the comment section of everybody saying, well, that's not AI, because you're not just feeding in the pixels like a human brain would receive, you're feeding in the positions of the objects. And I just had to take a step back and think, well, why on earth would you want it to read the pixels if you can give it the data? Right? We shouldn't be developing AI to solve problems that we can solve by coding. And so the different form that an AI or machine learning algorithm takes from a real brain is really reflected in that. Use the computers areas where computers are good at manipulating data. Let them manipulate data. Only use the machine learning part of things for where they're not good and where we don't know how to solve that problem. So.
Yeah, that's a really good example of, like, for example, the Google Home and Amazon Echo. Is there a combination of a lot of multiple narrow intelligences together, right? So you could build a system that looked at the pixels and figured out where things were at, and then fed that into another AI, right? And so when you combine different systems together, that is what that is one of the ways that architecturally that gives you the ability to do that. So whether you accomplish it through a neural network, a different way of acquiring the data, programming logic, etc. And again, this goes back to the thing that as we become more accustomed to technology, it's easy for us to say, oh, well, that's not really AI, that's not really magic, that's not really this, because I understand that, but I don't understand AI. So if I understand it, therefore it's not AI, it's not magic.
Right. And I mean, that comes down to application. If you have we're building a new war machine and we want it to go out and kill people autonomously, then the data it's going to have is going to be a bunch of pixels from its camera or some infrared data from whatever, right? So if that is the application, then it makes sense to develop the AI that can identify what's in that data. But if the application is to plan strategic planning, and you can feed in the relevant strategic data, then don't make it read pixels, because that's just, it's just wasting CPU cycles for a start, right? So yeah, it's about finding where that application matters and applying the correct algorithm at that point.
Yeah. There's a question here that I think kind of feeds into this. I guess it feeds into neural networks and some specifics, but it says, isn't AI really artificially intelligent without the ability to have and use memory of events and evolve memory as it learns? Now, correct me if I'm wrong, but I believe a lot of the neural networks, and I can't remember the term for it, actually are able to understand where they're at. Yeah, where it's at, have a memory, and then be able to apply that as going forward.
Yes.
Yeah,
Yeah.
temporal neural networks can do that, and they're form of recurrent networks. So one of the properties of recurrent neural network is the fact that it can remember where it was because it has a recurrent internal implementation. So it can perform things at a multitude of stages that it can create on its own internally. So that's one of the properties of a recurrent neural network.
So we should also bisect the question, because recurrent neural networks, yes, they have some, let's call it short-term memory of a sort. So they have feedback to themselves and short-term memory. But they're generally, their main sort of function in the problems that they solve tends to be problems where the size of the input data is not known. So for example, LSTMs are often used in parsing sentences, spoken sentences. And the reason why you need that short-term memory in that scenario is you don't know how many words are going to be in that sentence. You can't just feed in a vector of words that's a fixed length. You have to give it different sizes and then have it analyze the sentiment of that sentence. And so that's where most of these sort of temporal algorithms come from. But if what we're talking about is learning from the past, learning from previous seen examples, well, that fundamentally is what the connections in a neural network do. But they are one of the reasons why we don't tend to continually train neural networks is you can overtrain them for a problem, you can overfit, you can manipulate that memory internally within the network in such a way that it becomes less useful, which obviously is not a desired outcome. But there are algorithms such as Q-learning, which the way I like to think about Q-learning is imagine you are playing a game, you have a maze that you're going to find your way out of or something like that, and you need to decide at each intersection what your next action is going to be. Well, what the AI is doing is it's making a kind of a deck of cards, a memory of what the map looked like last time and what it did and what was the outcome. Yeah. And if it does that several times, it increases the score of moving north, south, east, west, whatever. So basically it builds up this deck of information that says, these are the scenarios I've encountered before and how they went badly or how they went well. And then you train it by saying, no, you did badly and punishing it, or yes, you did well. And that is, again, another form of attaching memory to a learning system, because you're attaching a previous wealth of knowledge of what it did before to the network. So it is completely untrue that the neural network has no memory as such. And where that myth tends to come from is this idea of fitting in classical perceptrons, because it is possible to overtrain it or to undertrain it, and it doesn't have, in the biological brain sense of the word, it doesn't have memory cells. It's just a neural network. But no, it's not true. There are several different types of memory now that we're introducing. And one last point before I let you move on. I was reading some research recently on simulating sleep in neural networks. And as it turns out, when we simulate the effects of sleep on neurons in neural network simulations, they learn more effectively. So don't think that the machines won't need to sleep. That's at least one thing to remember.
Actually, you need memory to build an AI. Without memory, you cannot work AI, because you need weights, you need activation value, and maybe you should also put a function, activation function. So this has a memory space in the memory of the PC, of the micro architecture or whatever. So without memory, there is no AI. But without memory, you can build AGI, artificial general intelligence, because it has the concept of the thing. You just connect the free memory, zero brain, and then AGI developing its neural network, neural things inside it. So maybe AGI cannot have memory, in my opinion, but also it should need some memory for some beginning things. For example, how he gonna give output or how he gonna get input. So these things needs another situation. So codes may be called like AGI, but the memory is also needed for neuron structures in all neural network artificial intelligence technologies. Sergey is sleeping, I think.
I'm not sleeping,
What do you
but
think,
guys,
Sergey?
you just jumped to such let's say a low level, because I thought that we will explain maybe people like how to start, what to start to use. Oh my God, yeah. This
Yeah,
is what
Actually,
I'm talking about. Yeah.
I do want to jump to some of your slides, Sergey. Here you had RPA. What is RPA? And I wasn't sure on that one. I wanted to ask you about that.
Yes, you know that we have this modern trendy word like AI. I don't know. So it was the Bitcoin, then it was AI, and right now it's like RPA. RPA like a part, some part where we can implement and apply artificial intelligence practices. RPA is like robotic processes automation. It's like a new approach of, let's say, for business programs, for business software, how to use all this AI. Because let's say I know such a little amount of businesses when they understand how to implement AI for their real business purposes. Because when we are talking, let's discuss, do you need any AI implementation for your real business, let's insurance company? They will say, what? It will be like, we will color the brain for the, you will create for this application. How to implement this? It's not easy. This is why we have this new approach, like robotic processes automation, like we are using AI for any business processes. And this is a new approach. For example, we are taking some Excel document, we have to analyze this document and do something. Before, for example, like 10 years ago, we used all the automation, just read the cells, get data, and somehow translate and process it, and you have a result. With AI, you have new approach. Like you have a system, AI system, where when you're given some information, we can recognize this information using computer vision or some other techniques, like in general, not like you will develop with the developer and try to parse some information. No, you have to use some vision, computer vision, analyze, teach, and describe some behaviors. And this is like a glue for all of these our AI technologies and frameworks for real business purposes. Like give some document, some integrator will teach how to work with this document from the vision point of view, like from the picture, not like analysis of something. After the vision, you can recognize the words, understand what does it mean, and process somehow using machine learning models and so on. This is what I wanted to add. As our RPI, it's like it's a modern world nowadays in all this real business applications.
Okay, great. So I actually wrote a tic-tac-toe is a really interesting example because you can write if then else logic, right, to implement tic-tac-toe as an AI, and I actually made a system it didn't know how to win tic-tac-toe, but it knew what legal moves were and what winning conditions were, and then would play itself with random moves until it learned the moves that were most likely to win. But you can do that, but it would do that by storing the entire board state of the entire process, which you can do with tic-tac-toe because it's such a simple game. But as soon as you get any more complicated tic-tac-toe, that becomes astronomical number of moves, like chess, for example. And so that's why
Yes,
chess
this
was.
is why this is available for us, because our computing resources are available for nowadays, like not like 10 years ago. This is why we cannot build these models, and why this is so popular right now. But yes, Jim, is it like Deep Blue computer, which like won from Garry Kasparov? It's Deep Blue. What's the name of the supercomputer?
Yeah, it was
Yeah,
Deep
it was
Blue.
Deep Blue.
Yeah,
Deep
Deep
Blue,
Blue. But here maybe it will be interesting for the participants, for the people, how to implement, how to use, how to develop this easy artificial intelligent game. Like, okay, like, because I think not a lot of people understand how it works at all, because we are starting to discuss high level like things like philosophical, let's say, issues, but a lot of people just don't understand how to implement it. Because and this is why I wanted to explain, like in simple words, like how it works. Just like, okay, because yes, we have classifiers, like this, but it's like next level of all this world. But like how would the artificial intelligence in simple rules? Like we have some rules. We describe but anyway, it should be like we have like an artificial intelligence engine, which in this engine we have to explain somehow such rules, some rules, and then we have to explain how to play, and this our engine have to play theoretically all games. It has to play. It has to teach itself. It will know all the results, and during the game with the real, for example, human, he will predict and use successful, let's say, game results, and it will work this way. And this, let's say, this is not something new nowadays, but it's just basic technique. But maybe we can, but we also have another approaches how to do that. Maybe instead of stupid just self-learning, maybe Boyan can add somehow how we can implement this, or Quake, or Yunmasuru. What's the other approaches? How we can use this in another way?
Well,
So,
yes.
you're welcome, Boyan, go ahead.
Yeah, if I understand correctly, the question you're asking how we can implement an engine that learns on its own how to, let's say, play a game. Is that correct?
Or maybe not like, maybe we have totally different approach for this tic-tac-toe game artificial intelligence. Not
Sure.
like play all games and remember all the results. Maybe we have some other approach.
We do have even today, effectively, let me think about that for a moment.
I know that if you're doing a neuro, oh, go ahead. I was going to fill in while you were thinking.
Yeah, you probably were gonna say something similar to what I'm going to say. Effectively, one of the type of classifiers, and again, I'm gonna gravitate toward the concept of classifiers. One of the type of classifiers are classifiers that can receive positive and negative feedback, right? So effectively, even the different backpropagation type of trainings of neural networks can be adapted to this approach. So in essence, if you have, if you play and you move in certain way, and again, you don't have to remember the whole game, and you probably will not remember the whole game because that's not how typically classifiers are implemented. But if at different stages you make moves, and if as a result of each move you get encouragement or punishment effectively, and if you start adapting your behavior based on this positive and negative feedback, you will learn eventually, you will evolve, and I prefer to use in this case the term evolve. Your classifier will evolve to the point where it will be able to play such game, even if you modify the general game, without having to learn and remember all previous games and stuff like that. So it will learn when it is at a certain position. That is example, if it is at this position, it is best to play here. Or if it starts, it is best to start from the center, obviously, because it gives you the most advantages. But it will learn that effectively, and I will use that term loosely, it will learn that intuitively based on the positive and negative feedback it has kept receiving as a result of making that move in the past. Okay, and that's somewhat similar to the way a kid learns to play the game. The kid doesn't analyze typically the whole game. The kid develops the intuition that when it moves, does a certain move, it gets a better chance of winning the game. So that's effectively a bias that gets developed by the classifier for a specific move. And again, I'm oversimplifying it, and I'm oversimplifying it on purpose, but that's how you do it without learning all of the back history of playing game, as Jim said. And I use the term evolution of the classifier, because that's been one area that I have wanted to research for a long time. And that is the area of merging neural networks, specifically recurring neural networks, with genetic algorithms to create a self-evolving and self-constructing neural networks. If we can achieve that, we will effectively have a quite functional model of a human brain or animal brain, effectively, because as the best of my understanding, not necessarily in terms of neurons, but in terms of connections between neurons in the human brain, the human brain reconnects internally over time, all the time. So it evolves. And my belief is that the human brain evolves as a result of external stimulus, positive and negative type of stimulus. If we can model the same thing with a self-evolving recurring neural network, we will be able to create a self-constructing, effectively, neural network that self-constructs and self-builds and self-trains based on positive and negative feedback. Then you will have effectively software that builds itself, per se, which is what we were discussing at the beginning of this session. So that is why I on purpose use the term evolving for the classifier, because that's the direction I think we should be taking for future of research of AI, if we want to create really self-evolving and self-developing artificial intelligence.
So,
yes.
What I'm noticing there, so what Boyan's done, Boyan has answered the problem of which algorithm would you use to address this game, this problem of tic-tac-toe. And I'd like to answer the question a little differently and answer how Boyan came to that conclusion, because that's basically where my learning has been over the last few years. So because I started studying neural networks by myself, for the understanding of how they work, what I've picked up on is which algorithms there are. Most of them, you know, I can name them. One of the names of them is actually slipping my mind right now, but I'll come to that. But what are the algorithms? What kind of problems can they solve? And then how to apply them. So from a practical, I want to learn to use AI technologies standpoint, what I would say that you should focus on is not necessarily learning right away how everything works, but learn what algorithms exist and what kind of problems they're applied to. And the reason is that this example, tic-tac-toe, can be brute forced. You can just stack all the different combinations and tell the computer which one to use. There are very few games for which this is true. This very quickly becomes a problem of scale. And so some of the more successful algorithms, the two that that Boyan mentioned there, reinforcement learning, the most popular reinforcement learning algorithm I think is Q-learning right now, and genetic algorithms, the name of the most popular one I forget off the top of my head. So Q-learning is effectively reinforcement. It's saying you did something wrong, change your strategy next time and try again. So it doesn't have to brute force the problem. The more you train it, the better it will be, but you don't have to give it every scenario. So for games like chess and Go, these have far too many combinations to brute force the problem. Q-learning or reinforcement learning is the way to go with that. Genetic algorithms generally, genetic evolution of topologies is coming to mind. That's neat. That's the name. Neuroevolution of adaptive topologies. Basically, what this does is it takes a neural network model and it's effectively a way of pruning the model or extending or pruning the model depending on what's needed to solve the problem. So it's an evolutionary thing where you simulate 10 different games at once, and of the 10 different games, you pick the top 3 neural networks, and you then sort of create offspring from those networks to genetically modify them and evolve them to solve the problem. But what's important here is that what Boyan did was identify reinforcement learning and genetic algorithms as the approach to take. And that's what, in my opinion, my experience is mostly academic. I've not done much practical, but in my opinion, if you're getting started in artificial intelligence machine learning, you should be learning how to tell which algorithms will solve the problem. Learn what these things are called, what are they good for, and understand that before you even start implementing code, because a perceptron could solve tic-tac-toe. But if you extend the board to a 9x9, the perceptron would become computationally very expensive. Extended again, it becomes even more expensive. So the perceptron is not the efficient algorithm to apply here. While it could work, it's not the best way to go. The best way to go is probably reinforcement learning. So learn that, learn which algorithms exist. And the other tip that I would put in here is I did a course for Code Rage 2018, 2019 on building neural networks from an engineering standpoint. And the reason that I did that is because if you go and look at the research papers on this stuff, unless you are a mathematician, you're going to be reading a foreign language. These things, you know, unless you read the mathematics, what does this symbol mean? You know, what's epsilon mean in the equation? Unless you understand all of that, you're going to be reading what feels like gibberish. It is not the place to start learning. The research papers is where you go when you understand the concept and you want to understand some detail, but you don't go there to start with unless you are just somebody who has a natural tendency for mathematics. So learn what algorithms exist. You know, Google's your friend. Find out what algorithms exist, what kinds of problems they're used to solve, and go from there. That would be my take on that.
Good suggestion. I do want to, real quick, we are running out of time, but I do want to throw this up here. Blaise Pascal Magazine, issue 87, 88, does have some coverage on neural networks, artificial intelligence as well. So check that out. We are past our allotted time, and I know a couple of you do need to jump off. I will try to skim through some of the questions here, make sure everything's covered here before I go at least. But I did want to thank everybody for being here and point out that we will have the slides. If you go to, there's a link here. Let me bring this back up here. On the website for this, which is right here, TCoffeeAndCode spring 2021, which I'll put the link in there in the chat as well. We'll have all updated slides. I'll encourage everybody, all the panelists, to go through and add resources. There's a couple slides at the end where you can add resources or add new slides if you're like, we didn't get a chance to drop into this. Yep, add a slide, put some more notes in there. And I definitely think we can do another beyond the content that already exists out there, like Craig referenced his code rage, which we should add that to the references as well. Resources as well. We can certainly look at doing more coverage on this in the future.
So will there be a replay on this?
Yeah, so there will be a replay available on this as well. So you can grab the replay, and I was just looking to see if I could find Craig's code rage video. I don't see that, but there are some other ones. If you look, there's the IBM Watson one. There's a couple from Boyan, and more. So yeah, there's some other videos out there on our YouTube channel, which I put a link in there. It's Embarcadero Technologies on YouTube. You can find us there. And yeah. So Sergey, I know you needed to go. Anything before you take off here that you wanted to bring up?
It was very great, guys. I don't know, we just passed, I think, 20% of the slides.
I know.
It's more than 2 hours. Yes. It was very interesting anyway.
I found it very interesting, and yeah, it would definitely be something I'd like to cover some more in the future. So
we should have episode 2 for this session, I think.
I was talking on mute there. I apologize for talking so much. I work from home from a basement now, so when I get the chance to talk, I don't tend to stop. Sorry for not getting through the slides.
Yeah, again, I mean, guilty as charged here as well.
I did put a link to the slides in the chat window. Also, I put the PDF copy in the handout section on GoToWebinar if you're on the GoToWebinar live session. But also, I will like I pointed out, that we will have an updated version on the website there as well. So if you check back there on I'll put the link in here for this.
I added a link to the Code Rage 2000, it was 2018 Code Rage, and another one to a recent post that I did on why Python is so frequently used in machine learning, which may be relevant.
Fantastic, yeah. So yeah, stay tuned to blogs.embarcadero.com or the embt.co/TCoffeeAndCode spring 2021, and I'll have some updates there. And then we'll try and get some more coverage on this, because we could go on probably another 2 hours just on the material we had prepared for today. So thank you, panelists. If you want to stick around, I'm happy to stick around and keep going with this. Anybody that wants to, I just know Sergey needs to go, and I know some of the people may need to go too. So
yeah, I have a day job, so I'm gonna have to drop.
Okay, all right, no problem.
Thank you.
Yep.
Thank you.
All right, let's see. So there's a comment here: intelligence is making a decision using new unknown data based on experience gained from old data. That is something, I mean, that is effectively what a lot of the narrow intelligence stuff is doing today, with where it's able to look at old data, old pictures, for example, classifiers like Boyan was talking about, and saying, oh, I know all of these are a cat, so therefore I can make the decision this is a cat, right?
Yeah, that's clustering, and in general, one of the areas where artificial intelligence has been particularly good is pattern recognition. So recognizing certain specific features and general patterns and stuff like that, that's area where AI in general has really shined.
Yeah. Pat says, excellent session. My brain hurts, but it was an excellent session. Thanks for thinking of putting this topic as presentation. Very big thanks to the panelists. Yes, agreed. Thank you everybody for being part of this. Yilmaz, I didn't get a chance to get to your slides hardly at all.
Okay, no problem.
Let's go ahead. So you have a few ones here. Some of the leading names in artificial intelligence. Do you want to tell us about some of these? I actually only recognized a few of them, so I feel kind of bad now. Do you want to tell us about what some of them are doing, and real quick?
Mm-hmm. I want to put these names, and there are many, of course, but these are helping AI developing faster by sharing a lot of things, papers, you know. And one of my favorites is Joshua Tenenbaum. He's working on AGI, what I am interested in since 19 years, in 19th, since from the 19th. And he's doing very interesting thing. He's investigating babies, kids, very small kids, how they react to actions, and they are researching this. And this is the true thing to search how we are evolving, evolving our things. And Yan Lesun, I am sorry if I am pronouncing right, Geoffrey Hinton and Yosha Bengio from Canada. They, you know, earned the prize in 2019, and yes, Turing Award. And they worked on the key developments of neural networks, and which are reshaping how computer systems are built. And also there is Andrew Ng. He's very well known. I think who is new here can find videos and courses about artificial intelligence. He's very loved by the course participants because he's teaching very from the beginning. What is AI? How is the beginning? How you calculate? How matrix convolution works, etc. And there was one more name, Lex Friedman, and he's working on Tesla, actually on autonomous vehicles and human-robot interactions. But he's doing something very good again on YouTube. He's doing podcasts like us, about 1 hour, 2 hours. I cannot follow all of them, but they are really amazing and giving very future ideas, because he's not talking with only computer engineers, neural network engineers. He's calling physicians, calling mathematicians, microarchitectures, but he's also giving a view from the how AGI or how we can evolve this AI, you know. So it's very priceless. I think all posts are very priceless and very brain burning sometimes, you know. Yeah, so these are my favorites. Maybe Boyan may add some new names, I don't know. Or
Yeah, unfortunately, as I said, I have been working lately largely on microcontrollers, so I was not able to follow that close the field of artificial intelligence. I am now getting back into it for a variety of reasons, including because I want to port some of the code to microcontrollers so we can have artificial intelligence in Arduinos and ESP32 and ESP8266. Oddly enough, it is actually possible to some extent. So for that reason, I'm starting to look again, but I will not be able to offer any names. I think you did very good job on this. And I see, by the way, that there was a specific question for me in the chat. If you don't mind, I'll answer it.
Yes.
Roland was asking if 10.4.2 version is released. I released the first beta about 2 days ago, I believe.
Yeah.
A day or 2 days ago, I lost track of time a little bit. I'm already working on the next beta, and hopefully within the next week or so, there should be an official release. In this release, 2 of the files turned out to be damaged. Signal Lab and Instrument Lab has been damaged for some reason, the zip file. All the other zip files are fine, including Intelligence Lab. Also, MegaLab contains all of the libraries. So if you download MegaLab, you get everything, including the Instrument Lab and Signal Lab that the single installers have been, for whatever reason, damaged. So again, there is a beta already available. The beta is in very good shape so far, spare these 2 damaged files. And the official version, the new beta and the official version are also on the way.
Fantastic. Yeah. I put a link into the release there.
Thank you.
There was a comment here about AI not being suitable for things beyond tic-tac-toe because they're too complicated. What the comment was, what Craig said is that it depends on the algorithm. So one type of algorithm may work for tackling tic-tac-toe, but that same algorithm doesn't scale to more complicated games. So if you look historically, we could use one type of algorithm to solve tic-tac-toe. That's something anybody can write using a linear if-then-else logic. And then they used a different type of AI, Deep Blue, to solve chess. But then it was AlphaGo that solved Go via artificial intelligence. And each of those represents exponentially more complex games. So that's kind of what they're saying. Each one of those implemented different types of AI, different algorithms. And so it's really a matter of picking the right algorithm. And that was one of the things Craig was saying is important if you're wanting to learn artificial intelligence is to learn the different types of algorithms. On the resource.
Yeah,
go ahead.
I just want to inject. What you said actually matches exactly what I said historically. You actually went exactly to the history of development of AI. Expert systems are exactly what you described. Expert system, you teach if else effectively logic up to very big extent to solve the problem. That was the belief in the 80s that with expert systems we can achieve that. And no, they do not scale, which is exactly what you pointed out. And yes, we evolved to nowadays use classifiers, and classifier-based AI now can play chess and Go and so on and so forth, and obviously even beat us on this. So artificial intelligence algorithms are suitable for any purpose. Don't get me wrong about that. There is no exception. They're suitable for any purpose. It's just a matter of whether or not a specific algorithm is, and again, algorithm is not the right term. A specific type of classifier is suitable or not for the specific term. And the reason I moved away from algorithm is that classifiers do not necessarily need to be implemented in algorithmic form anymore. That's a whole different topic. But for that purpose, I don't want to use the term algorithm. I prefer to use the term classifier when I'm talking about artificial intelligence and type of classifier.
Okay. Yeah, great. I think so. It looks like people are dropping off, and I'm not seeing as many questions come in. So let's go ahead and wrap this up, I guess.
Okay.
And thank you, everyone, for being here. And let's do this again. Clearly, there is interest in it, and we did not get through everything. So, yeah.
Thank you.
Take care, everybody. Thanks for being part of this.
Goodbye. Thank you, Jim. I appreciate it
Bye.
for organizing it. Goodbye.
My pleasure. Bye-bye.
Bye-bye.